Welcome to Lecture 11, Scanner Design, Chapter 8, Part B, Lexical Analyzer Scanner Design. So in the previous lecture, we talked about how to design a Elixir, a lexical analyzer, and we come up with the rule of how to convert a finite state machine to convert it to a lexical analyzer. And we also talk about a maybe table-driven way to do it. Okay, so today we are focused on how to use tool and table-driven way to do it. But before we go into that, let's actually learn what's compiler design automation. That's called compiler CC. Okay, and then yet another compiler. These are already very mature tool, okay? But it's very powerful, so here we still look into it, okay? And then we have Lex, Yet, or Flex and Bison. Lex is the original name for the lexical analyzer. Yet is yet another compiler. So this one is a parser. And Flex is implementation of the Lex on the window. Bison is a implementation of Yet on Windows. So these two actually are also Lex and Yet. And then some people design a PLY, okay, Python, Elixir, and Yet, okay, Python Lex and Yet. That is Python version of Lex and Yet. Okay, so these are the tool and its relationship. But we will look into the C version of the Flex and Bison mainly to talk about this compiler and talking about how to use it to generate the so-called lexical analyzer. So we will also talk about how to design regular expression and putting the regular expression into lexical analyzer's automation. And we will use an example of a simple pre is Python Lex and Yet scanner design that match text to generate token. Okay, so these are the basic concept. So before we get started into the regular expression, let's look through the theory of Lex and Yet. So before 1975, writing a compiler is very time-consuming task. Okay, so it takes a lot of time. And then implementation details for Lex and Yet may be found in these. Okay, so basically, Flex and Bison are clones for Lex and Yet for the GNU and also for Windows. Okay, this actually is a graphic Windows. So Cygreens is a 32-bit Windows port of the GNU software. So you can see this is Win32. Okay. And then whatever, okay, so it actually is a minimum GW environment. You can run the Flex and Bison, okay? So Flex and Bison are what we want to use. And in fact, our course, we do cover this before. So basically, if you go into the older course image, so let me actually try to find the older image. We do cover this before in, I believe it's 2017 or 18. We actually go over this before for the whole Lex and Yet, okay? So let's look at the course. So the course, let me bring up the master shell. So here we do have 8 week, okay, this one is older one. So here they are 2017. Let me look at this one. 2017 is actually, okay, this different by Python. So basically right here, you see, we do look into the lexical analysis and Flex and Bison and calculator. So just look into the 2017 recording session. You should be able to see the past recording for these lectures. So anyway, here just trying to say that we actually have something recorded before. And let's continue. So basically, the idea of the Lex and Yek is that let's assume that we have some language and we do lexical analyzer using Lex. So we design some sort of regular expression and we call it pattern. So regular pattern being fit into the Lex, and Lex will generate some lexical analyzer. So your input language will be converted to tokens. And tokens, we have token, and based on the context-free grammar, you generate some parser, and then the Lex will be generated, the tokens will be used to convert it to syntax tree. And this syntax tree you can be used to generate the assembly code, the executable code, or can be evaluated for the result using the interpreter. So here, these are the structure for these. So basically, the step one is to write the Lex file. So Lex file, the pattern will be written into some sort of Lex file. So let's assume that here we have calculator language that Lex. Okay, it can be that LEX or that L. And the Flex version is using L. So let's assume that we are using that L extension. And that file will be fit into the Lex, and then it will generate some sort of C code and being combined to lexical analyzer. Okay, so that's the step one. So basically, that is the .l file or .lex file. Okay, the lexical analyzer matches string in the input based on your pattern. So you need to design pattern and convert a string to tokens. And tokens are numerical representation of string simply processing. And when lexical analyzer find identifier in the input string, it enter them into simple table. So this actually just saying that you will create something into simple table, and then simple table obtain information such as data type and location of the variable in the memory, and it will generate a related simple table. And then next stage, you have the context-free grammar, and it's called .y or .yek file, .y or .yac file. And that file, you basically feed it into the so-called yek tool, and you generate a parser based on this, and with the help of Lex, Flex, and you will generate the so-called a parser. And parser can convert things into parsing tree. Okay, and you can be used to generate a in the C program, you can generate a compiler. Okay, so basically that's the purpose of generating syntax tree, and then you can go code generation. Okay, so basically initially you have if you have the combined Flex and Yex, you can use the calculator that Yek rule that actually is the context-free grammar, and you will generate the context table. So here you have simple table. And then you use Python.d, okay, -d. Python-d, you will generate a y.tab.h, that's an include file. And you can include that into your compilation for Flex, and that will generate a so-called ef.yy.c. This one is the Elixir. This one is the YY, the so-called ef, the parser. So these two combined together, you will generate a compiler or interpreter. If you combine the two as some functional, and your program, calculator program, can fit to the program, and you will compile to .esc or compile to assembly, or being directly interpreted to get result. So that's the theory of the so-called Flex and Yek. So first, let's look at the specific pattern matching the rule for Flex. Okay, so the lexical analyzer. So you can use Python-d call.y, and then that's generating the table, okay, calculator table, and also generating the Yek function. Okay, and then you use Flex to generate the lexical analyzer. Okay, and then you combine the lexical analyzer and the parser to create a compiler. Okay, so this is the project design process using the so-called flex and Bison together. But you can also use the flex by itself to generate a token analyzer. Okay, you can also use only the Lex portion. Okay, so Bison read in the grammar description in Y calculated the Y, okay, the EF file and generate syntax analyzer parser, and in that is in the function of YY parse, okay, and YY parse is in the calculation.table.c file, okay. So dash D option calls the Bison to generate definition of tokens, press them into calculation.tab.h, okay, and first read the pattern description in calculation.l, including the file.h, generate a lexical analyzer. So this type of lexical analyzer will take into account the program structure and the push down automatas feature to create more decent lexical analyzer. So finally, the lexical analyzer and parser compile and link together to create executable file. That is a compiler, okay? And from main, we call the YY parse to run compiler. Function YY parse automatically call YYLex to obtain the tokens. Okay, so here there are some reading you can look into. So first, let's look into the next portion. So during the first phase, the compiler read in input and convert string to source token. So that's actually is a lexical analyzer. And this portion you can be standalone. You do not need to use Bison to generate the table. But of course, the Bison portion will take into account more of the grammar issue. But if you only have the regular expression, using Lex is good enough, okay? And Lex can generate that allow it to scan and match string in the input. Each pattern in the input, the Lex will associate with some action. Typically, an action return the token that represent matching string for subsequent use in the parser, okay? Initially, we'll simply print the matching string rather than return a token value. So there's a directory printing or directory execution or maybe return token value, okay? So token value, we'll talk about it later. The following representation of simple pattern composed of regular expression, a scan in ID, and Lex will read in this pattern and produce C code for a lexical analyzer, the scan identifier. So here we have a very simple description of Lex. So basically right here we have a later, okay, this is an ID. ID is a later and later or digit. So basically you have some later, okay, and digit or later, okay, repeat, this is the ID, okay, so the ID. So the pattern matching the string that begin with a single letter followed by 0 or more letter or digits. This is called a ID. So repetition, we use a clean star, okay. Alternative or option, we use bar, okay. Concatenation, you just put them after it, okay. So, and parentheses for grouping. So this will build a finite state machine. You start from state 0 and you have a later, and then you have later or digit you repeat, okay. And when you see a space or something that terminate your string, okay. So this one is the so-called ID, okay. So-called ID is a finite automata. And this thing, if we actually use it, and we can use the so-called ad hoc algorithm to generate a lexical analyzer, okay, that we demonstrate before. But here, now we can easily understand Lex limitation. So Lex cannot use to recognize nested structure such as parentheses, because if you just have it alone, you cannot do it. So some nested structure, you will have to use the Bison with flex to do it, okay. Only Lex by itself, it doesn't recognize the nested structure, okay. So that you need to, if you have the nested structure, you will need to go back to using the Bison and flex together. Only by using Lex itself, you cannot achieve that purpose. Okay, so network structure handled by incorporating stack. Stack we call it push down automata. When we encounter, we push it to stack. So basically, Lex doesn't have a feature. Since it has no stack, it is not well suited for parsing network structure. So yet, augment and finite state machine that has a stack. Okay, so yet or Bison has the power, but Lex has limited power, and the difference is in the network structure and parentheses. Okay, so let's look at the no stack case with the Lex. Okay, so first one, you need to know about the .l file. This one's .l file. That's a regular expression file. Okay, you write your regular expression in the .l file. So that you need to study the regular expression. So later half of the lecture, we will study how to write regular expression. But at this moment, let's assume that we know it. And we are only studying the process of how to use regular expression to write the next program. Okay, so here we do have the basic rule for the regular expression. So single dot means matching any character. \n means a new line. Star means one or more, 0 or more. Plus means one or more. Question mark means 1 or 0. Cap means beginning of the line. $sign means end of the line. And then A or B, okay? A, B, one or more time. String or literal of A plus B, okay? And then break it for character class or option set, okay? Option set, character option set. Okay, anyway, so regular expression, you can write ABC, that mentioned ABC. ABC, C star, so 0 or more C, okay? So here we have some rule. So right here, I don't repeat it because in the last lecture, we already talked about it. So now, there are YY Lex, there are YY wrap, YY out, YY. These are different functions and symbols that will be used in the next. Okay, so let's look at first one. First one is a symbol called echo. So echo will directly just write the match string. Okay, this one is a special symbol in Lex file. So echo is just echo a later. Okay, echo later. A begin condition is like switch starting condition. Okay, initial start condition. So in the Lex file, you have a YY Lex file. That is the final function that generated for the Lexer. Okay, and then there is a star YY text. That's the pointer to the match string. So you match some pattern, it will point with the pointer that pointing to that string. YY length is the length of the match string. Okay, so you may have some regular expression pattern. Say you have a program. Say I'm matching ABC. Okay, and the pointer pointing to this matches ABC, okay, that is called YY text as a pointer, okay. The length of this match string is called YY length, okay. And a value associated with the token, okay, value associated with token, so you can evaluate it, and that value, left hand side value is called the YYL value, okay. And YY wrap is wrap up if actually return 1 if done, 0 is not done. Okay, this one is wrap up, whether it wrap up or not. And the output file is YY out, input file is YY in. These are the your text input and output string file or something, or token string file. Okay, so that's the first program structure. They are separate in 3 sections. Okay, they are separate in 3 sections. And the 3 sections are separated by percentage mark. Okay, so section 3 is user program. So you put your main function or something over here. Okay, and part 1 is actually definition. Okay, so input to Lex is divided into 3 sections. The percentage sign divided into 3 sections. This is the best illustration example. The first example is the show. This is the possible Lex file. That's a percentage. Okay, that actually just saying that that's a Lex file. And input copy to output one character at a time. The first line percentage always required. So percentage is always required. And the minimum file that you can allow for this is actually percentage, okay? Okay, so here actually, however, we don't specify any rule, then the default action will be used, okay? So if we don't write any rule, so part one is definition, part two is rule, part three is your user program. Okay, so let's look at a simple example. So right here, part one, we don't have any definition. Part one, we don't have any definition. Part two, we look at a single letter, we do nothing. And then \n, we do nothing. Okay, main program, we do nothing. So this thing actually will be, this one is for flex 0, okay? So let's look at this flex 0 example, okay? So let's look at the flex 0 example. So this flex 0 example, let me use print up my window R, okay? So let me cd to the location. Okay, dir, we are here, just bring up the code, okay? Bring up the Visual Studio Code. So here we have a .l file that's actually is a dual file. So section 1 definition, we have nothing. Section 2, we have \n, we do nothing, okay? Section 3, we have dot, okay? We have a dot. So we basically also do nothing. It's a semicolon. So these are dual, simple dual, and you do nothing. And main function, we do nothing, okay? So this one, let me take out this YY file to here, okay? YY file here. So we only have this right now, okay? So let's do dir. At this moment, we have nothing there. So that's actually wrong flex. Okay, you need to install the flex first, okay? The installation will be available, okay, in our start portion, okay? So let's do this one. We actually have the flex function, and we do read in the flex 0.l file. Okay, let me see. It actually doesn't have the flex. Okay, I do not have the flex program. First one, we need to find the package. So to find the package, you go to your means location, okay, and then try to find how to install it. So here we have pacman-s flex. So let's copy this one, okay, and go back to here, right click, paste it, okay. So let's push it, okay. You start to install the flex. I just proceed with Y, okay, every time. Okay. In addition to that, we would like to also install the so-called Python. Okay, so let's actually look at the Python. Okay, so Python, we need to have a pacman Python, so let's actually copy it as well. So go back to this MSYS2 here. So right click, paste, and then hit return. Okay, also proceed with Y, okay. So Python also got installed. So right here, we do not need this window anymore. So after the installation, we still cannot use our flex and lex. That's because that normally our G++ is under this min GW64 bin, under your min sys 64. Okay, but the flex and Python is not there. It's actually under this min sys 64 USR bin. So let's look at it. It actually is over here. So we need to add this one into our path, okay, into our path. So right here, you do have a Python over here. Okay, you do have a Python over here. And here we also have a flex over here. We do have this two thing over here. We do have a flex over here. So it is already there, okay? This different program already there, okay? So we can use them. So let's actually copy this path, okay? Copy this path and then go to our advanced system setting. So right here, we have system. And here you say advanced system setting. And look at your environment variable and update your path. Okay, so create a new path that put your directory. What that means is with user bin and click OK, get out of here. So now we need to go back to our fresh directory and create a window R again, with number command line, and then left click, copy this one, okay, do CD space right click, go to here. I'm sorry, not this directory. I go to the wrong directory. Let me go one more. We want to go to the fresh directory. Should be this window. So let's copy this one. Okay, I'm sorry. Go back. Copy this one and CD to this directory. Okay, so right here we can run fresh. Okay, make sure that we have fresh0.l over here. And we have space and fresh0.l. Okay, it's wrong. So after it's wrong, a fresh lex.yy.c lex.yy.c will be created so that actually open it. So open it actually is a C program. Okay, it's a C program. So let's look at it. This one is a C program, and it actually have the so-called YY. Let's actually look search. There's a YY Lex. Okay, there's a YY Lex function that you can use. Okay, there's a YY Lex function that you can use. Okay, so that's that. So how about main? This one, because you do not specify the user program, so define in main function. Let's see, do you have a main? You don't have a main function, okay? So actually there is no main function in this one. So this one can only be it is created just to verify the feature of the YY, okay, the Lex function. So let's delete the older version, okay? Since we exercise it. So go back to our slides, okay? So that portion actually nothing. So let's look at the first number one, okay? The first one, just to create the YY Lex function and not really useful. So let's look at the first number one. So first number one here, we have an executable file, we have YY Lex. So right here, let me actually delete the executable file. Let me take out this YY Lex to outside as well. So we have a first number one. So let me change. So let me change the directory to there. So CD label up and CD press 0, press 1. So dir, we do have this, okay? So now let's look at this file. This file actually, in the definition portion, we have nothing. And if we see a dot, we echo. If we see a backslash n, we also echo. So these are actions that will be taken. And YY we actually will return 1. So this will return 1, as we mentioned before. Return 1 is in the table here. YY return 1 if done. Return 0 is not done. Okay, YY see if the program done. So you need to have this program YY, okay? And your main program just run one YY flex, okay? Just do YY flex. So right here, let's do this, okay? So here, let me actually change my directory over here. So let me get the folder to this one. So I can have this flex number one. Okay, this is the program over here. So now over here, we see this one. Let me close this one. So right here, I'm going to run flex and then flex1.l. Run it. You generate a file called yylex.c. So that actually here we do have this one. Let's actually open it. Okay. I'm sorry. Let me use Visual Studio Code to open it. So here we do have a program. Okay, we do have a program. And this is yylex.c. So let's look at it. Because there's a main program, okay, so that here let's actually do select find, okay, so let's find main function, okay, let's try and find main function. Okay, so we do have a main function, so it actually is the so-called wrap up portion, so it's a yylex. So we do have a main function like this, okay. So let me actually try to get the calculator file to here. Okay, so let me copy the calculator file from the previous example to here. It's in demo. So let me look at demo 10. Okay, so we do have the calculator language file A and B. Let me copy them. Okay, and put into what? Put into let's do this, okay? Let's do this. I don't want to use the Python format, so let me actually directly. So let me create a demo 11, okay? So at this moment, let me put these two files over here, okay? And what I would do is actually, I probably don't want to modify my setup in my Python too much, okay? My Python example too much. So let me do this. Let me go back to my this one. Let me go back to my Python directly. Okay, going to my C. Okay, so flex 0 we have this. Okay, that's okay. Flex 1, let me put back. Okay, we do have this. Okay, so let's continue to do GCC. Okay, and let's have this one called what? Called lex.yy. Okay, so this one is lex.yy.c-l. Okay, Elixir. Okay, let's actually do this. Okay. Okay, finish. Okay, so we do have the Elixir file. So this one we actually finish. Okay, we finish. So let's don't actually change it. So let me actually copy the whole. This is a different flex file. Okay, all of these flex file. Let me copy all this flex file to my demo 11. Okay. And then let me put these two calculator files into flex 1. Okay, so flex 1 just compile them. So let me actually change directory from here to here. Okay, so I'm in the flex 1. So right here, I'm going to do Elixir, okay. Getting the input from my a.cow. Okay, so basically you will echo every later. Okay, echo every later. So let me do Elixir, and then from b.cow, you echo every later from b.cow. So this one is the feature of a simple echo using the flex function. So we finish the so-called flex number 1. So one thing is very important is that if your section 1 user program, you do not put anything there, it won't work. So you must put your main function. You must put your main function in there. Okay, and so basically right here, this flex number 1. The part 1, we do not have anything. The definition, we do not have anything. Rule, we check for a regular expression of that will echo. Change that will echo. Okay, so that's a 2 rule we achieve over here. Command line, you use a /*. Okay, these are command line. And then section 3, the main program, you put in the YY wrap. This one is necessary. You cannot do without it, okay? And then you have a main function over here, okay? So these two, we use them, and then we use the flex, and you generate this function. So this function is a result that generated from this flex1.l file. And we basically use that to create a executable file. And that executable file called Elixir. And the Elixir, we need to take some input. But I do not take the input from the console. I take the input from this HR file. So I need to redirect the file from a.cal. So if I don't actually take it from the other file, I take it from console, you should have, say, I am Eric Chow. Okay, it echo. This is a program. It echo. Okay, how are you? It echo. Okay, and when you finish, you use a Control Z to finish the terminate the input string. Okay, so let's try one more time. So this Elixir actually is a repeater. So next, this is a good program. You will echo. So the echo function just echo every single letter you have. And at this moment, Elixir is still listening to it until it meet the end of file, EOF mark, okay? But this one, you can also redirect your console from a.cal input file. So in that case, the a.cal file being fit into the Elixir, okay? So Elixir is a function, and here we demonstrate the basic feature of how to compile a flex file, okay? Now let's look at how this program works internally. So two patterns have been specified in the rule section. Each section must begin with a column 1. So you must begin with column. You cannot move to leave some space. So basically, you put the so-called regular expression over there. So you have one dot, that's regular expression. You must line up on the column 1, and it will do echo. Echo is a macro code. We explain the macro code. So here you have a \n. Okay, that's actually also do echo. And there are two functions in your program. One is YY-less, one is the YY-wrap. YY-wrap is a requirement, so you must put it here. Otherwise, it won't work, okay? And the purpose of the YY-wrap, you can search the internet. Okay, you can search the internet for the purpose of the YY-wrap. So the YY-wrap, let's see. Okay, let's actually search the internet. So there's a YY-wrap is meaning of the YY-wrap. So YY-wrap actually, when the scanner receives end of file indication from YY input, from your console or from your a.cal, then you check the YY-wrap function. At that time, you check the YY-wrap function. So let's look at our YY-wrap function. So the YY-wrap function right now, it will automatically return 1. When end of file, you will wrap up, you'll do some wrap up. So this one actually is the end of the program processing. But you can choose not to do it with no YY option. There's a no YY option you can set before everything, before the so-called rule section. You put into the definition section, you can put a percentage sign with the no option and then no YY-wrap. Then the YY-wrap requirement will be waived. So this YY-wrap is a requirement that you need to provide. Okay, basically when the file ends, you will run this YY-wrap and you will receive 1 if actually it finished. And YY-wrap will return 0 or false, then you will assume that the function had gone ahead and set up YY-in to point to another file. So it may go to another file and the scan will continue. So it will go on to several different files. So continue, and it returns true, then it actually ends. Then the scanner terminates and the 0 will return to the caller. Okay, so that's the purpose of the YY-wrap. YY actually is something that you can write. You can modify the function for the YY. Okay, so that you can check how YY is operating. If you finish a file, you may go on to the second file, third file, fourth file, and that's the wrapping function. You can continue that. Okay, so that's the purpose of the YY. And you have the so-called echo. An echo function is basically a F write. So you write to the file using this YY out to write it. Okay, write to the YY out at this moment, and then actually you will do this. So basically this one is a function. It's a function. So it will replace the echo. So echo is a function here. And okay, so basically these two are two rules. If you match the regular expression rule, you'll do this action. Matching this one, you will do this action. Okay, let's go back to the program and look at one option. Okay, let's go back to the program and look at it. So go back to this demo 11. So let me go to the first one. So right here, I have the first one. So this first one is what? It actually is echo. So let me copy this file. Okay. Let me copy this file and then let me actually create a new file. Let me post over here. Okay. And this one, let me save as. So this one, let me save as. This one is fresh, okay. Fresh one, okay, and new. Okay, so this one is fresh one new .l file. So you need to, because you want it to be the less file, so you need to save as all types, okay. So something like that. And right here, our section 1, right now, we will try percentage sign option, okay. No, let me see. It's no wrap, okay. So actually, this one, we should put option, no YY wrap, okay? So it should be option and then no YY wrap. Okay, this is the option I want to have. And then there's an integer count. So this integer count is the basically the counter, okay, it's a counter. So it's a counter for, so percentage curly brace, these two portions are the internal declaration. Right here, I don't do it, okay, I don't do it. But here, I don't like the echoes. So here, I'm going to give it a different function called print f. And here, let's actually say x, okay, let's print out x, okay. Print out x, that's a later x, okay. And then this one, actually, let's actually print. Okay, this one that's actually print f, okay, and here that's actually print out new line, okay, and this one we will put actually change line, okay. So let's look at this subversion and this YY wrap because we went the YY wrap requirement, so let's actually delete it. Okay, so new one will be like this. Let's actually save. So let's save. Okay, save this one. And then let's go back to our window. So right here, go back to here, and I'm going to compile the program. So it's a flex. Okay. So now it's actually calling the flex one. Okay, new.pl. Okay, finish. And the next one it has the program. It's a program right now. It's actually called YY Lex. Okay, this one's still YY Lex. In the same directory. So this one already overlapped the one that we have for the Flex one. So this one, let me actually call it a different name. Okay, I'm sorry. This is okay. Because we need to continue. So right here, let's do this GCC. Okay, Lex. Okay, that actually YY. Okay, this is Lex.YY. C, okay. This program is called Lex.YY.C, okay. So let's start yy-c and then this. Oh, this one is actually put it to the Elixir new. Okay, Elixir new. Okay, finish. Now I run Elixir new and I get it from a calculator language. So you see, it actually print out SSSS for every letter, and then it print out new line mark and change line, something like that. So the last portion, there's no new line mark, so it actually just finished the program. Let's print up our a.cal. So a.cal here, let's compare. This one is the comment and new line mark, comment and new line mark. I'm sorry, here you have the data and the new number, and this one actually is the end of file. Here we do not have any new number. So now let me return one more and save. So let's try one more time. Okay, so right now this one, it has the new number. So this actually is a good example for telling you what you need to do here. So basically, this one is the regular expression pattern. This one is the action that will take. Matching that, you will do this. Matching that, you will do this. Matching that, you will do this. So Luo action. That's what we have here, okay? And basically, designing the Elixir is something like this. We will tell you what we can do later, okay? Using this Elixir program. So that is the function. So here, let me do this, okay? Here, let me actually put a extra directory. This one, let's put a new version, okay? And let me put this this one here, and then YYLex to be in the new version, and Elixir new also in there, okay? So here, let me keep the original version on top. So right here, later I'm going to zip this file and share with you. So I'm going to do this way. So let's do fresh, and then actually this one is fresh1.l, okay, and then we do gcc, okay, fresh1.l. I'm sorry, this one should be lex.yy.c-o, okay, lex. This one is the previous version, so let me keep it in this way, so we don't actually have conflict. Okay, so when you download a file, remember the new version have the collection of the new version that I wrote with the action function of different type. Okay, so that one is the fresh number one, and we actually know that the function echo is actually calling the function that writes something to the YY out. Okay, so basically we are operating on these different internal data structures. Okay, we are operating on these different internal data structures. So that's the fresh one. Now let's look at the internal structure. Basically, you have the YYLex that will every time you take a token pointing to the new location. So it is advancing the YY text location to this point. So it keep running this one, but whenever you ask for a text, the YY text will take one token at a time from here. Okay, take one token at a time from here. And then that's the lexical analyzer. And YYLab is another one that when you finish the file, you will continue or not continue. That's the purpose of the YYLex. And then here you have more of the internal data structure that you can use, okay? But the main function is like this. So the rebel YY text is a pointer to the match string, so or token. YYLex is how long it is. YY out is the specified output. And default is go to standard out, okay? YYLex function is called when fresh, when the input is solid, so end of file, you return 1. When you are done, 0, you continue to process more files. And ABC program requires main function. So you write the main function in your application section. In this case, it's simply called a YYLex, and each time you get the character. Okay, so that's the first example of this flex function. And we modify with the no-wrap. Okay, we modify with no-wrap. So let's look at this one, flex number 2. This one, actually, you will find each string, no matter how many characters it is, we will print out the line number and the text you got, okay? You print out the line number and text you got. And here it has the argument vector, and the argument vector 1 will be the file name. So you've opened the file. So this one, you no longer need to use the file redirection mark. And you actually can use it, and then you will take the token out, and then at the end you will actually print out the YY.in. Okay, so that's what we have here. So let's look at this number 2. So the number 2, let's go to the directory. So here, let me go to the flex number 2 again. Right here, let me delete this Lex YY that we copied before. So let me delete it, and then let me take out this one, and also take out the flex 2 program. Okay, and let me go to there. So let me do cd going out, cd flex 2, okay, and dir. So we are here, and then actually right here we would have we will do flex, okay, flex 2.l, okay, and then this time we again compile it, lex.yy.c, okay, this all, this one is actually also called Elixir. So you will create a Elixir program, and this Elixir program, we were still using the a.cal. So let me copy the a.cal and b.cal from the project 1. Okay, paste over here. Now this one, we do not need to actually use a redirection. So here we would use a.cal. So you add the line number and then the so-called things over there. Let's check it. Let's check it. So let's open the a.cal. So a.cal here, actually it missed something. So look like the data has not been initiated. So the line number started with 1. Let's go back, okay? Let's go back. Go back to our fresh open. Let's actually go back to the fresh 2. Okay, so right here it has a value of this, and you will increase, then it will print it. Okay, so right here, let's actually set this one to 0. Okay, initial value, set this one to 0. Let's try again. Okay, let's set the initial value line number initially to be 0. So it increase every time we had it. Okay, so let's try again. So flex, okay, flex 2.l, and then here do gcc, okay, lex.yy.c-o Elixir. So redefinition of the y external YYLens. Okay, here let's see. It has a redefinition of the YY line number. So here, let's see, YY line number. Let's see. That's actually that this one should be an internal data structure. So let's don't move it. Okay. So let's do this the other way around. Okay. Instead of using plus, let's actually put the plus over here. Post equipment. Okay, one more time. Post equipment, one more time. So here that's actually wrong. Flex 2.1. And here let's do GCC lex.yy-c-o Lexer. Let me do this. Okay, let me do this. Let me actually go here. Let me delete this YY-lex. Okay. Okay, one more time. Let's actually here. Let's actually save all. Okay, we already set. So let's do one more time. Flex 2 L GCC lex.yy-c-o Lex. Okay, so Lexer, and then we run the a.call. So this one you do not need the redirection, and you go back to 1, 2, 3, 4. Okay, so that is some multiplication that I have. This one actually is the demo program 2.1. It demonstrates no ref function and also the line number increment. And next one, we go to this one called flex number 3. This one, you will count the number of the character, and each character can be lowercase or uppercase later. This one actually is a pattern of ID, so we will see the ID format. Okay, ID format is you start with lowercase or uppercase later and followed by letter or characters. So this is the so-called ID. So let's actually look at the ID version over here. So now let me go to flex number 3. Okay, go to flex number 3. So here, let me delete these 2 files. Okay, I back it up just because that in case that I lost it, I still can move them back. Okay, so let me move out of flex 3 and YY-lex. Okay, move out these 2 files. So I'm going to change to that directory as well. Okay, over here we have the flex number 3. So we do flex, okay, and then flex 3.l, and then let's do GCC lex.yy-c-o Lexer, another Lexer version. Okay, now let me go back to the flex 2, copy the a.call and b.call to here. So this one will be counting the number of the so-called ID. So here, let's do this one. Let's do Lexer and a.call. Okay, so total identifier are 8. Let's look at the a.call and look at it. The a.call has 1 ID, okay, 2, 3, 4, 5, 6, 7, 8. Okay, so a.call have a ID like this. So let's actually try different way of okay, here actually that is the flex 3. We will try different way later. Okay, let's see. Let's continue to move on to flex 4. So this one counting the character count, word count, and line count all together. Okay. So here, when you have a \n, you increase the line count and character count. When you see a white space letters, you increase the word count and character count, and also when you see a normal character, okay, and then you increase the character count. Okay, that's it. That's the character count, line count, and space word count. Okay, so this one calculates 3 different types of the counter. So these 2, let me also delete them. And I'm going to the flex number 4. So again, let me take out the flex 4 execution file and YY-lex. Okay, I'm going to delete them later. Okay, so right here, right here. Let me actually first bring up this flex number 4. So this one is counting the character and the word and how many lines they are in the file. Okay. So let me actually try this. So let me go to here. Let me actually cd flex number 4 dir. So here we see flexible 4. So flexible 4.l. Okay, and we do gcc and then lex.yy.c-o and then Elixir. And then with Elixir, okay, we still need to copy our a.cal to here. So copy a.cal and b.cal to this location. Okay, good. Now we do Elixir and then we put space a.cal. Okay, so that's the number of line, that 4 line, how many character and how many words. Okay, so that's that. Okay, and that's the number of word count. And we still have number 5 and number 6. Let's actually look at the number 5, number 6. So open the flex number 5. Flex number 5. Let's see, look at it. Is it checking the digit and the ID count and later? Okay, so digit is defined as this. So you see the digit is what? A non-terminal term that you define in the definition section. So right here, instead of using single character, you can combine certain pattern, regular expression pattern as a certain name. And that's a name you put into curly brace. So this term, you put it over here, the curly brace, that would be a digit. And the later will be like this. And this one is an ID. So that is a ID. So this one is the term. Okay, this one is the term. And then count is the number of the count of the later. So that's actually checklist number 5 as well. So let me actually first pass the A-cal, B-cal into the number 5 as well. Okay, and take out the flex number 5. Also take out the YY. Yes, okay, this one we can replace it, no problem. But basically, we can just take them all out. Okay, basically we can delete that. So here, we are in here, flex number 5. And let me do CD and CD flex number 5. Okay, and we do flex, okay, flex number 5.l. And then we do GCC, okay, and then lex.yy.c-o Elixir. Okay, and we do Elixir, and then we do a.cal. Okay, you find out identifiers. This one, you find out they are A identifiers. Let's go back to number 6. Number 6 is actually way bigger, so we will not demonstrate it. Let me create another one. This one called flex number 7. Let me use a flex number 7. So here I'm going to copy this flex number 5 from here to flex number 7. Okay, and this flex number 7, I'm going to rename it to flex number from flex number 5 to flex number 7. So here we have a count. Okay, we have a count, and this one that actually see this one is a count. So you will print out the number of identifier. Okay, so that's actually here put it as ID count. Okay, this one let's put it as ID count. So besides that, that actually try to match different way. Okay, match different way. So we will have a dot, we do nothing. So this dot do nothing, we don't want to use it. Okay, let's go back to our example in the previous lecture. So let me bring up the slides from the previous lecture, lecture 10, tokenization. Okay, so in the tokenization, we do go for such a state machine, okay, such a state machine. So let's look at this one now. Let's look at this one now. So basically here we have a different pattern, okay. So let's try this, okay, let's try this. So here, if you have A to D, we call it digit. If it's later, we actually call it later. So before this rule, let's do this. If we see a parenthesis, okay, a single parenthesis, then we do one thing, print, okay, print F, left parenthesis, okay. We do a right parenthesis. So here, these two actually are, I think they are using for group, okay, using a group later, so that actually put the backslash. These are group letters, so let's put it in this way. And here let's print right parenthesis. Okay, and the plus sign has special meaning as well. That actually print. This one is plus. And minus sign. I said minus sign is okay. We will know, we will learn pretty soon. These are token IDs, okay. So here, this one, we print, increase the ID. We also do print let's actually put them into a cobra. So here we will print ID. Okay. And then we have time. And this one we will call it times. Okay. Then we have a division. Division is this one. Okay. And division has no special meaning. So let's do print division. Okay, then we need to deal with the command. So command, you actually may see a pattern that's start like this, okay? And then here you should have multiple words of that. Okay, so this one is actually backslash star, okay? Backslash star. And then here you should have multiple words, okay? And then you have a star, a slash, okay? This whole thing will actually print out comments. And if you have slash, slash, okay, and this one will print. And then slash slash followed by one or more words, 0 or more words, and then followed by backslash n. This one will print comment too. Okay, so you deal with ID, deal with commands, deal with the parentheses, deal with plus sign, deal with minus sign, deal with time sign, okay? And we also will deal with assignment. Assignment is colon followed by equal. Okay, that's actually assign. Then ID we deal with already. Next one, we are dealing with dot and digit or more. Okay, so here we should have a dot. Dot is backslash dot. Okay, that's a single dot. And then we should have digit. Okay, single or more. So it actually should have plus sign. Okay, that's a real number. And you may also have digit. Okay, this one, same thing, it will be one or more pattern. This one should also be print. This one should be integer. This one should be integer. This one is type 1 real number. Okay, there's another one, actually, it should be digit. Okay, one or more, followed by a dot, followed by a digit. Okay, one or more. And this one we will print. This one is actually real type 2. Okay, any other letter we will do nothing. Any other letter we will do nothing. And these are the pattern we collect right here. Okay. Okay, so right here, let's actually save this one. Save this one as our phrase number 7. Okay, and then we do CD up and then CD phrase number 7. Okay, now I need to actually copy my Lexical over. Let me go to my phrase 4. Copy the Lexical and Lexical over. Go back to my phrase 7. Okay, good. Now actually we got it, and then let's do phrase. Okay, and then phrase 7.L. They are unrecognized dual in A9 and 1415. So A9, 1415, let's look at it. A is this one, it is actually unrecognized dual. Unrecognized dual. Okay, let's see, it actually unrecognized dual. A914 is a single start. So this one we need to do this. 15 we actually division, so let's actually have this. I think that actually that's because it's a slash, maybe need to have a backslash. Okay, let's actually try put that in. Okay, let me try one more time with this. So save. Okay, save. One more time, let's do it. Okay. So let's do phrase, okay, and then phrase 7.L. Okay, pass. Now let's do GCC, okay, and then let's .yy.c-o, okay, Elixir. So we print out count. So count actually we don't have the count. So right here, let's change to ID count. Okay, ID count. Okay. So in between you token out, okay, you will actually token out. So let's actually try one more time. So here let's do rex, okay. Rex 7.l and GCC last YY.C-O Elixir. Elixir and then a.cal. So as you can see right here, let's actually look at our a.cal program. This is b.cal, I'm sorry. Open a.cal. So a.cal program is right here. It started with a comment, and then there is a change line mark, so there's nothing. And then right here, you do have ID, assign, integer, comment 2. Okay, and then ID, assign, integer, comment 2. And then actually C, okay, C is ID, assign, left parenthesis, ID plus ID, right parenthesis. Total ID count is A, B, C, A, B. So only when ID happen. So this one, as you can see, it is a Python a Flex version of the tokenizer. We finished that, and you can tell the difference between comments and the ID and different ones. So this one, actually, as you can see, is more systematical way of designing the so-called Elixir, and it also can replace the ad hoc solution for scanner. And you can see that the efficiency of writing such tokenizer is actually much higher than I use my my ad hoc scanner, writing the ad hoc scanner. It is actually more productive to do it in this way. Parsing of tokens, extended vector normal form. Up to this point, you may have already realized that using the regular expression to process the tokens would be very efficient, and we can use the so-called Flex Python to help us. And you have the tokens, you have an input file, and you do use Elixir generates the tokens, and then we pass it into the process. So the Elixir portion, you can write it into the regular expression, and then use the Flex to help you to generate the Elixir. Okay, that's what we already demonstrate. You can also draw down the finite deterministic automata, and then you design your own ad hoc scanner or Elixir. Either way is fine, but we believe that this way is easier when you do prototyping. Overall performance, maybe the ad hoc design would be better. And so it's very important that we need to study the regular expression to be able to design the Elixir. So here, actually, the regular expression and counter-free grammar are used in scanner and parser. So basically, you design the regular expression, okay, and then present it in DFA, and it is using linear structure, no step, and you will determine the structure of the token, okay. And parsing, you will need to have step and parsing tree, so it can be recursive, and so it comes with stack, and the grammar is counter-free grammar. But that's another issue that we will do later when we design parser. So Becker's normal form, it has sequence, choice, option, and repetition. This choice is using a bar, option using bracket, repetition using curly brace, okay? So here are some forms that we use, okay? And this will be later used in Python or different language. We will explain it. Here, so this is the EBNF. At this moment, just remember here we have something like this. Okay, in the Elixir, we only use the so-called regular expression, and EBNF will be used in counter-free grammar. We will talk about it later. And okay, this is EBNF, and here you have the equal concatenation, termination, and option repetition, different thing. Okay, we'll come to this IEEE standard later. So these are the grammar for the EBNF. Okay, we'll come to this later. Okay, now let's look into the regular expression. So regular expression, in the previous lecture, we already talked about it. There are a few functions usually we will use. One is the match function. Another one is the replace function. And another one is the split function. And also find function. These are the typical function we use using regular expression on to do text processing. And we need these for the design of regular expression for next generation. And we also demonstrated on our website, there are some regular expression editors. So you should try the online regular expression editor. Make sure that your expression is correct and you can apply it to the so-called program in the Elixir design. So here, first, single dot means matching a single character. A bracket means there is a collection or a set. So A-E-I-O-U means these 5 symbols are vowel sounds. These 5 symbols are vowel sounds. A cap means that the reverse of it. So A-E-I-O-U-Y, and cap means that any letter but not these. Okay, that's a not negation operation. Dash is a from, so from to. So from 0 to 9, it actually is a range specifier. And anchor, you have the cap means the beginning of the line. $sign means the end of the line. So regular expression, you can have concatenation. You actually have regular expression A followed by regular expression B. That's called concatenation. A or B. So regular expression A or B. Sometimes you have the parentheses just to group them together to avoid the confusion. And R question mark means that 1 or more time for that regular expression. R star means 0 or more time. I'm sorry, question mark is 0 or 1 time. Okay. R plus means 1 or more time. RM with curly brace means that M times. RMN means match it M to N times. And R question mark, okay, this actually is some combination of it. Okay, so parentheses and parentheses are pattern. So parentheses are used for grouping, okay, grouping. So grouping some certain things together, that's actually to grouping when you use the parentheses, okay. So parentheses R means match R and the delimitary group. So it's actually grouping this together. And you have the regular expression R, okay, and you have the question mark P and name. That means that there's a pattern grouping, okay? So matching R and remember the match text in group using the name. So there's a pattern name, and that is, you find out the regular expression that is, you're putting into a certain grouping name, okay? And question mark column is match R, but not remember it, okay? This one useful when you want to determine the minimum number, no redundant group, okay? So here this is specialized grouping notation. We will look at it when we see the real example. Okay, so question mark P equals name, match the remembered text with the name. So you match with certain grouping way, okay? Match equal R, actually match a regular expression and don't remember the text, okay? Makes a question mark, exclamation mark means not equal, something but not equal. So here this regular expression with group is actually a little bit tedious and only when you need it, okay? Dash means that, okay, not, okay? So here match itself if not in the bracket, okay? So special character, so that matches literal. Okay, this one is, so this portion actually is the grouping and regular expression. Next one is escape later. So escape later, if you have \d means the digit. \d, capital D is non-digit. \s is white space letters. \s, capital S is non-white space letter. \w, H is the alphanumeric ID use letters. \w is H non-ID use letters. Okay, and you have A plus will be equal A star, that's equivalent. A, B, C, D, E, you will equivalent to A bracket B, C, D, E. A, R, 0 or 1 means R, 0 or 1 time. Okay, bar, vertical bar is the OR operation, okay, optional. So in Python, we know that A star, B plus C star, star perform before plus. We say star is actually higher precedence over plus, okay? We could be implicitly and write down this, okay? And the sequence of precedence is lower than the precedence of postscript, okay? So basically we have AB star and AB parenthesis star, it is the same, okay? So sequence precedence is lower than the preceding, so question mark, star, and plus, it actually is lower in precedence, okay? So all higher precedence than or actually is of higher precedence. Okay, these are just some rules, okay? So here we have kept A or B, so A or B in a line, and it only has one letter of A or B, okay? So this one is a line with A or B. And this one is either your file start with A or your line ending with B, okay? These are different, okay? These are different. You start with A or you end with B, okay? Okay, anyway. This portion, you have the cheat sheet, okay? And you have another version of explanation. This one we just skip, okay, skip. And let's look at the match function. So regular expression, you can include from, import from the so-called RE, okay, the regular expression module for the match function, and you will return an object, okay, you will return an object. If they return no object, then it actually is not matched, okay? And when you return with the object, the match object is a result, and you can look at the result object's contents. Okay, so right here, you actually have a match Python with Python. You return a match information object. So this match object is a match information. If it's none, you do nothing, okay? Otherwise, you say matching is true, okay? And you print Python matching with the result, okay? So that actually Python matching with Python is true. Okay, and then you match the Python star and the Python is found, okay? And then these two actually matching object is false. Matching that star is actually 0 or more letters, actually is true, okay? These two is true. So left-hand side is pattern, right-hand side is string, okay? So next one, you matching the Python star with Python is found. Okay, this one slash dot is single dot, okay? Single dot, we do not have a single dot, so that actually is false. So next one, we have, okay, Python slash means single slash, okay, means single slash. So single slash dot and star, it actually is false, okay. Next one, we have space, okay. Space one or more is actually is false. One or more space, actually, this one is true. Okay, so this one using the RE to match. Okay, let's actually try this one. This one is a very simple combination. So let's actually try to open the folder. just try to use it. So here we are in, we would go to our demonstration directory. Demo 11. So we have so many flags. So let me create first one. Let's call RE. RE means that I'm using the RE module. So open it as a directory. So this one, let me actually create something called match.py. Okay. So here, in here, you actually can import. So import RE module. Okay. So right here, let's has a string s equals A, B, C, D, E. Okay. We have a pattern. Pattern equals A star. Okay. And here we will have the match. Let's call it match object. Okay, match object will be equals RE the match. RE the match my pattern with my string. Okay, and then let's print out my match object. Okay, let's print out my match object. So you get a match object. Okay, you get a match object. Okay, it's like this. Okay. Match the A, that's the your match. Span is 0 to 1. 0 to 1 means starting from 0, ending at 1. Okay, that's the match object. So you got a match object. Okay, so here if we try have another string called no matching object that actually is B, C, D, E, F. Okay, and no object equals read.match. That there's no match, and we print no object. Okay, and the no object actually is none. No object actually is actually no match. Okay, no match, no match. Okay, this one is 0 or star. Actually, there's a match. There's a match. Okay, there's a match. So let's see, 0 or more. So let's actually use the plus sign. It's actually one or more. One or more, the second one will become none. Okay. Now we got this MO object. So let's actually look at the. Okay, let's look at the so-called Python RE.match. Python RE.match, you return the match object, and the match object actually has many different things that you can actually look at. Okay. So there's a group 0. Okay, group 0, you can print out a group 0. Okay. That's actually try, there's a group 0. Okay. Group 0, you actually will print you the matching group. Okay. So let's see here. Let's actually go back to here. Okay. So here, let's actually give a MO. Okay. So print the MO that group 0. Okay. And group 0, and you also have a parameter of span and match. Okay. So let's actually do this one. If actually MO, okay, print MO.span. Okay. If MO, okay, print MO.match. Okay, these are different parameter you have. Okay, so let's actually run it. Okay, there's no such thing as match. Okay, there's no such thing as match. And we do print out this one, and then MO.match. There's no percentage. The span is an object. Okay, span is an object. So that's actually convert this object to tuple. convert it to tuple. And the match, we do not have match. Okay, so let's do this. There's no such a thing as it's not iterable. Okay, the thing is not iterable. So that's actually, it's not iterable. Span is not iterable. So that's actually print out is 0. There's no such thing as 0. Okay. So that's just print out is span. So span is an object. Okay, so you print out the group 0 that actually is A. Okay, and then, oh, it's a method. Actually, it's a method. So that's called a span method. And span method return an object. So let's do this. Okay. So let's do this. Let's actually use the T tuple equals the match object that span. Okay, and then print the tuple. Okay. Okay, let's try this one. If MO, okay, then actually string, okay, X, okay, X equals MO.match. Let's try this, okay. So there's no match object, so this one doesn't work, okay. But we do, we can actually print out the so-called tuple. So we can print out the tuple is like this, okay. So let's actually try this one. We print out tuple and let's print out the so-called S. Okay, so we print out the S and then tuple 0 to tuple 1. Okay. And that's also getting an A. Okay. So this one is the idea of using the match function in the match function in the RE module. Okay, let's continue. That one is one example. So next one is we can use the match function for many purposes. Now we need to design the regular expression pattern. Okay. So let's assume that we want to design something called July 4th, July 4th, July 4th, and July 4th. Okay, this different pattern. Okay, and let's look at it. Actually, you have the July. So JUL. Okay, and you follow by Y or no Y, right? You follow by no Y or Y. So it can be no Y or Y. Okay. So if no Y, okay, let's assume that it's no Y. No Y, you can actually be followed by 4 or false. 4 or false. Okay. No Y, you follow by 4 or false. So this one is no Y. No Y, and you will follow by 4. Okay. And false. 4 false is 1 or nothing. Okay. 1 or nothing. So basically, you go to here, you have TH. But this TH can be bypassed. Okay. And then with Y, you actually will follow by, okay, I'm sorry, right here, no, it's here you should have a S, okay, a space. So July followed by Y or followed by S, okay, followed by S, you you are okay. Followed by Y, you follow by a S. Okay. And after that, you would have 4 and actually 4 TH and 4s and capital 4s. Okay, 4 possible way that you can do. Okay, 4 possible way you can do. So with the space, okay, with the space, then you can start with 4, okay, and also followed by TH or no TH. This is one way to terminate. The other one, you can use F, or you can use a capital F, and you followed by ORTH. Okay, so this actually is the state diagram. Okay, this actually is the syntax diagram that we will get from this pattern. That's the syntax diagram we get from this pattern. So basically, you have this one, July, followed by a space, okay, 1 or more, and then 4 and the optional TH, okay. This one, July, followed by Y, okay. And then here you have followed by space, okay. And then you follow by 4 with optional TH or F with TH, okay. So this one, you can look at it in the 4th of the July 4th, the PY, okay, in the sample code. And we have the pattern written down in this way. There are different ways you can write it, okay? This is not the only way you can do it, but this one is one of the ways you can do it. Second pattern, okay, let's look at the 12-hour clock. So you have 5:09 a.m. or 11:23 p.m., okay? So let's look at this one. This one, actually, you can have the hour. The hour, you can have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. Okay. So basically, you should have 0, 1, 2, 3, 0, 2, 3, 4, 5, 6, 7, 8, 9. And then one you can have single 1 or single 1 followed by a 0 or 1 or nothing. Okay. These are single letters. This actually is 1 or these. And these are optional, okay? Okay, optional. So that's actually is the hour. And minute portion, you are starting from 0 to 5 and then 0 to 9. Okay, these are the minute session. And these are AM, PM, you have A or P, okay? A or P, and with M, okay? So the resulting regular expression will be like this, okay? You can have actually 0 to 9, okay? This one should be 0 to 9, okay, 0 to 9. 0, 2, 3, 4, 5, 6, 7, 8, 9, or 1 followed by 1 followed by nothing or 1, 1, okay? So this is slightly off. This one actually is slightly off. Let's write this clock measurement, okay? Let's actually try this one. Let's create match time. So here, I also import RE, okay? So the pattern should be equals, okay? You can have 0, 2, 3, 4, 5, 6, 7, 8, 9, 10, or, so here you have or, okay? Or you have 1, okay? Or 0, 1, okay? And this one is 0 or 1 time, so question mark. Okay, so let's look at this one. This portion, you have two parts, right? Two parts. So you have actually, you have two parts. So let's do this, okay? Here, this 0 is not necessary. So here, let's do this one, 2 to 9. 0 and 2 to 9, okay? 0 to 2 to 9. So basically right here, you have, you can have 0, okay? And then 2 to 9, and then possibly 1, and 1 may be followed by 0, or followed by 1, or followed by nothing. 3 options, okay, 3 options. Okay, this 0 or 1 time, okay, 0 or 1 time. So 0 or 1 time of these, okay. And then this one followed by a single colon, okay, followed by 0 to 5, okay, followed by 0 to 9, followed by a or P, okay, followed by N, okay. So that this is the pattern. So if you don't trust this pattern, let's do this. If you don't trust this pattern, let's copy, okay, and then go to the regular expression checkers that we used last time. That we actually used these before, okay? So right here, let's do 3:24 p.m. one match, okay? And let's try 0, okay, 2, 4 a.m. match, okay? 12:20 a.m. This one actually is a match. It is a match. 12:1 followed by this. Okay, this one 0 to 9 actually. 0 to 9 actually. It is okay. This is a match. Okay, 1 is not included. 1 is not included. So as you can see, it's actually matching the second part. It doesn't match the first part. Okay, it doesn't match the first part. So this one we need to have the whole thing be matched. Okay, we need to have the whole thing be matched. So that should be a whole token. So right here, let's add this. So this no match. Let me see. That is no match. Okay, let's actually see. Let's see. Regular expression boundary of words. So boundary of words, word boundary. Backslash B. Backslash B. So boundary of word is called backslash B. So here, let me try. Okay, let me try boundary of B. Boundary of B. So these two match. This one doesn't match because we don't have the 12. So that's the pattern we should use with the boundary of B. Okay, you must match the boundary of B before you can work on it. So let's actually do 12:00 p.m. This one is not matching. Okay, and then 1, okay, 60 p.m. It also doesn't match. 1:59 p.m. This one match. Okay, so this one is basically a working pattern that is, okay, let's copy back to our string over here. Okay, so that's the pattern. Okay, and now let's create a different pattern. So here, let's go back to our slides. So we do have this different thing. Let me copy the list over. Okay, copy the list over. Put it over here. Okay, and then let's do for, okay, time for t, okay, time t in list. Okay. Okay, just do this. Whatever matching one, we will actually print it, okay? T is a string. Let's actually print T first, okay? See if we get a T, okay, from the list. Okay, we actually have 5 different patterns. So that's, don't call it list, okay? Don't call it a list. Your list will be overwriting something, okay? So these are 5 different patterns. So we read a match, okay, that's actually here, let's do MO equals this, okay, match object. So matching your pattern. So this one match, okay. So here print mo.full0. No, it doesn't go in. Okay, it doesn't go in. So let's see here. Let's actually try. Let me try outside. Okay. Let me try this one. Don't use T. Okay, let's try 1:20 a.m. See, we got MO. Okay. Actually, MO. Okay, MO is none. MO actually is none. MO actually is not matching. 1:20 a.m. Boundary. Let me take out this boundary. Okay, so it matched now. It matched now. Okay, so I mean, in different systems, they may have difference. Okay, they may have difference. So this one, let me comment them out. Okay, in different system, they may use different way. Okay, so the boundary, word boundary, work for the website, but look like the word boundary doesn't work for the Python portion. Okay, anyway, sometimes you need to do some experiment because each installation may be different. Okay, so here, this one, we have the clock. Okay, This one is digit. Okay, this one 0 to 9. So here should have 0, 2, 3. It should be 0, 0, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so let's actually make it a little bit bigger. Okay, something like this. Okay, and this one is 0 or 1. Okay, but it's optional. So we do 0 or 1. Question mark. Okay. Okay. So here we try to show you the matching of the pattern. And there are more practice that you can work on, okay, because we have limited times, but there are several different pattern you can work on in this problem set, okay, in this slice. Okay, there are several different problem you can continue to work on, okay. And that actually right here, I don't go into those detailed discussion of each method. So now let's look at next one. The current example we are using the regular expression modules function, and you can also have the string operation. So string operation is that you can do match, okay, pattern with some string, okay, as a matching the pattern and string. You can also work on, okay, this one working on the pattern and string, and you can also do search and then a certain text function as a search function, okay. So search function, you search for VI and other words. So VI something, so Vela will actually valid, okay, valid actually will be matched, okay. So we can do match actually this A plus B or 1A or more A, okay, will be matched. And this one doesn't work. So this one actually should be, this matching should be what? Should be a totally match. Totally match. So this one match already is a boundary. Okay, it's already using the boundary. Search actually has no boundary. So right here explain why in Python, the RE module, there is no boundary, okay? Because matching function by itself is matching a pattern with boundary, and search is no boundary, okay? No boundary means that if it happened in a part of the word, search will work, but match doesn't work, okay? And you can find all of the occurrence of a certain pattern, okay? This is also search, but you will find all of the occurrence. Okay. That's find all. And find iterate. Find iterate means that you actually will return a iterable object, and then you can use the iterable object to get it one by one. Okay. To get it one by one. So that is the iterator, and you get it one by one using for loop. Okay. You go through that. So let's look at this one, iterator and going one by one. Okay. Each one of them you have the star. Okay. Every time you find iterate. Okay. So let's see this one. So here let's do find iterate. So here let's do import RE. Okay, let's assume that our string would be actually A B A B A A A B A A B B B A B A B B A. Okay, something like that. Our pattern that we want to find is AB. Okay. So now we want to find iterate. We want to find iterate. Okay, next one we want to find iterate. So we will do finding some pattern and then you return the iterator. Okay, you return iterable. You return the iterable, so we will do this. So iterator actually is a matching object. Okay, each one of them is actually is a matching object. So we do tuple will be equals iterator that finding the span. Okay, and we actually print the iterator that put below. Okay, we also print the so-called T. Okay, that would be a span. So we can also use its star. Okay, let's look at this. Okay. So that is actually each of the matching. So let's try a different way. So here we can comment these two out. Okay. You can check the starting location and ending location, but you can also print out the span. The span actually tell you both the start and end already, and they are in the tuple. Okay, so something like that. Okay, these are the location of the ABs. Okay, so that's the how you use the find iterable using in here. Okay. Okay, finding iterable, and then you can split with certain pattern. You get a string, and you will actually split with certain pattern. This one we don't spend time to talk about it too much. Okay, you can do experiment on it. And substring substitute is replace. You can replace certain pattern with some result. Okay, let's look at this one. Substitute. So we do substitute. So right here, let's actually do substitute the pattern from the string S, okay, with KK, okay. So look at the grammar. The grammar is the replacement and then text, okay. So pattern with replacement. So KK should go first. And then the text you want to be replaced. So anywhere that there is AB is replaced by KK, okay. Anywhere there's AB have been replaced by KK. This is a substitute using substitute function. So here you see we go into the find iterable split match search. Search is searching without boundary. Match is match with boundary. Okay, this different function in the regular expression module. Okay, and there's also a substitute the substitute n, okay, n actually is recent sub, okay. This one substitute n, okay. Substitution send a sub but return a tuple, okay. You return tuple instead of returning the result of the substitution, okay. And overlapping, okay, this one you can study it, okay. Next one is a regular expression object, okay. So regular expression module, it will actually create, it will work on a certain operation based on the regular expression given, okay. But the regular expression, you may use it later for different time. So you can use a compile the pattern, and then you create a regular expression pattern. And that pattern later, you can use for matching for different functions, okay, for different functions. So the same function used in previous string function can all be used. So let's actually try to use this one called compile, okay. Let's use a compile. Compile is to compile the regular expression object, okay. So here is still import, okay, regular expression. So here, let me use the one in this one here, okay. So let me copy this whole thing and put into compile, okay. The only difference here is that originally you do the find iterable whatever, right, or substitute. So right here, instead of using pattern, we will use what? This one actually is RE pattern. RE pattern is equal RE the compile. We're using AB as the pattern that we use, okay? And we create a pattern object, okay? And using this pattern object, we will do what? We will do RE pattern that match, okay? Okay, so here it shows you that, okay, the replacement work, okay, replacement work, okay. And we create a matching pattern using AB. So the AB is a pattern, and you will match and try to substitute with KK, okay, from the S. So you make the pattern reusable using this compile, okay, using the compile. Okay. So let's look at it. The same function is the same. It said that previously we need to call the IE.match, IE.substitute many times. But right here, you can compile it to an object, and then you can use that object match data. So basically this one originally used the re.match, but right now you can use the pattern regular expression, and then you create a pattern, and the pattern can be used many times for matching. So either you call it right away or you create a pattern to use it. There are two ways you can use the match, okay? So use the compile pattern for matching something, okay? So these are using the pattern, So patterns function are the same as the RE's functions, okay? It's the same, almost the same. You can study them, okay? So far, we introduced the use of the flex and lex to generate a Elixir and regular expression rule. So we also introduced how to study the regular expression rule and then how to design it. So basically here is a summary. So for the study of Elixir, first you need to study the regular expression. So you try to study the rules that you have. And in study of your rule, you can look at the regular expression editor to test out its validity. And then you collect that regular expression rule and its possible action that you will take and put them into your flex files. And you can use that to generate a lexical analyzer. Besides that, if you want to handcraft your own Elixir, you can come up with those regular expression rule, and then in your own program, you use them to into the match function, the find function, the find all function, the find iterate function, the substitute function, the so-called search function, and the so-called split function. There are several functions that you can use to design your own Elixir without using the auto lexical analyzer. So here, let's actually go back to some fundamental about the design of the regression rule one more time. So last time we go into the example 1 and 2, problem 1 and 2. Problem 1 on July 4th patterns. Problem 2, we work on the clocks. So here, one thing that I would like to say is like, starting from the idea, you need to analyze the problem or the so-called pattern that you are studying. And then the pattern, you need to describe it using syntax diagram. So something like the syntax diagram, and syntax diagram will look like this. And then from the syntax diagram, you start to write your regular expression that actually is corresponding to this syntax diagram. That would be something like this. That's your syntax diagram. And then find the proper function to run it. And to find the proper function, you have two ways you can do it. One is you use the function from the regular expression module, RE, or you use the regular expression module's compile function and keep the regular expression pattern into there, and then you create the pattern object. And the pattern object is representing the rule. So basically, it represents certain rule, and that pattern object you can run match against any input you have. So basically you use your regular expression pattern and actually compile it into some regular expression object. and use that. You can test against any input you have and performing your own function. And here can be metric function, can be substitute function, can be search function, can be any function that you like to have. So right here, let's actually go back one more time. So problem 3, if you want to design the phone number, so the phone number, let's assume that it actually is the one with area code and the one without area code. So the normal code will be 3-digit followed by dash followed by 4-digit. So this portion you can draw a simple 0 to 9, right? And then a 3 times followed by a single dash, okay? And then followed by 0 to 9, and then 4 times. So that's this normal phone number. And then you need to design your long distance call phone number. So it actually is 1 followed by a dash, 1 followed by a dash, and then the parentheses, and inside here you have 3 numbers. 3 numbers you have 0 to 9, and actually 3 times. So this is the way you design your regular expression, and you can draw it down as this. You can draw it down as this. You can draw it down as this. This is actually your inter-office. It is single digit with a few digits, okay? And that's one thing you can have. If you have inter-office, you can write down like this. If you don't have inter-office, you can combine these two in one stage, okay? And with international code, you go this format. So coming out your syntax diagram first, and then put that into your regular expression format, okay? So that's the way we design the regular expression. And the function, you can use the regular expression module functions, and also you can compile it into a pattern, and then find a function from the object and run it. So this, we already go over it. And here there are something that I will skip. So now I'm going to jump into the overview of the Python Lex and EX, okay? Today we are focused on the Lex portion. And this tool in the lecture 14, we will review it again. But here, basically, it is a tool similar to the flags that we use in C language. It's similar to this one. But here, this is a Python Lex and EX. Is the Python version. And basically, it uses the LR parsing, and LR parsing we'll talk about it in later lecture. So it provides a standard Lex and EX function in Python, and you do not need to use a separate Lua file. You can put them into Python programs. So print including Python.py, Lex.py, the token generator, and EX.py. And you can find the project from here, and you can install it. And this is the installation guide, just pip install print. Okay, you can install the package. So this is the install image. And then let's look at a simple calculator language that we have. Look at the next portion. So Lex.py is used to tokenize the input string. And it is a module that you can import. So you can actually pass in such thing into tokens. Okay, so it would be ID equals number plus number times that parenthesis ID minus ID parenthesis. So this will be the token result. So here you may generate such pair ID and the token type and token value, token type, token value, token type, token value, something like that. Okay, so So this one, actually, if you look into the Lex format, they are single standalone token, such as number plus time divide, left parenthesis, and right side parenthesis. These are token, and we can call this as token type. So token type is in tokens tuple. Okay, so token tuple, you can list down different token type. And then each token type's regular expression, you have the regular expression like this. So this one are standard, the single bubble type. Okay, if you have plus sign and you determine that it's a plus sign regular expression. So these are single regular expression. No rule one, single simple one. And if you are number, so this number actually you have the regular expression of the following digit one or more. Okay, this is number. I think this one is an integer type. So if this is an integer type number, the recursion is put in over here, and you put the t number. T number will be the recursion rule for the number. And instead of putting a single symbol, here it has this, and then we will evaluate the value, okay, equals the t the value. So here you pass a tuple, and the tuple will evaluate the tuple portion. Remember that eventually the token will have the token's type and token's value, and token value is a string. Token's value is a string, so that value would be converted to its value, and then the token will be returned. Okay, the token value will be evaluated. So you will get to such a format. The next format, the next result would have this: a tuple, type and the type and value, type and value, type and value. It will be like that, and when it is evaluated, it will become this. So this one, you can look at it as dual. The dual is the pattern type is \d, and the action portion is actually getting the value of the tuple's value. Will be evaluated like this. Okay, and U-line mark, it is one or more \n. Okay, and then it will actually evaluate the value of that token. Okay, and then the line number will be increased by the number of the token value. Okay, so the token value is new line mark. Let's look at the new line mark token. Go back to here. We don't see it. Okay, this one we don't see it. So you increase the number of the line number. Okay, and if it's tab or space, these are considered to be ignore type characters. So here you see some are basic simple. You will determine the type. And you will directly go to the type symbol. Go to the type symbol. Say here you go to the type. Okay, go to the type. If you have this such a dual, single dual, you would do that. If it follow the dual of the regular expression like this, and then it will actually determine the tuple value, and you get this. Okay, and the T ignore type is this white space later will be ignored, and then there's error type. If the token is error type, then it will the Elixir will skip it. Okay, so these are the basic rules that you use to design the Lex, and this portion is similar to this file, the so-called Lex file in Flex. Okay. But in Python, you can just write in Python format without separate file. And then here you use the lex.lex. Okay, you need to import it. You need to import the pre.lex as Lex. And then here you have the Lex module and you run the Lex function. That would be your Elixir. That would be your Elixir. That would be the Elixir using the previous rule. And then you can test it. When you test it, you prepare the data. And then Elixir is the Elixir that you have. You put a string into there. And then while true, each time you take a token and then get a token. If it is not a token, it's finished. So you break, you get out. Otherwise, you print the token. So this one, we can run it. Okay, this is a lexical analyzer, we can run it. So here in my lecture 11 example, I have the Lex example. So right here, let me hit the window R, bring up the command line, and then do CD, and then copy this path, and then put it over here. And we run code that. Okay, over here we have this one. It's called calculator lex.py. It import the Python lex, okay, and tokens is the token types, okay, token types, and these are the rules, token rules, okay, and here are some token rule with actions. And then the input, it build the Elixir, and then you prepare the input, be into the Elixir. So this portion is the execution part. And that's actually run this one. So let's actually get the terminal. So the terminal right here, we do have Python, and then run this one called calculator. And it run, and it gets such result. Here is a Elixir token number, and this. Okay, so let's look at the so-called input. The data is over here. You have 3, okay, 2, 1, okay, plus, okay, 2, 3, okay, and I think this one is a line number and column number. Okay, 2 and 1 are line number and column number, and then number 4 is 25, times is 27, 10 is 29. Okay, and then plus is column 3, line 3. Okay, line 3 and 314. Okay, something like that. Okay. So these are different token type that we generated, and it is saved in this one called calculator lex.txt file. Okay, so with token type, value, and something like that. Okay, so this one is the result. It's the result of the tokenization from there. So each time you run it and you get this. Okay, this one we do not evaluate it, but we will generate such token type and the value of the tokens. Okay, so that is an example of the Lex. Okay, that's the example of the Lex. Then we have another example. We don't go into the full length for it, but this portion including the so-called evaluation for the parser and evaluation portion. Okay, so this one is called calculator.py. It has also had the tokens, and you can run and get result. So the token type are these. Token rule are here. You have plus, minus, and then there's the ID. Okay, ID is here. You have the letters and letter with digits, and this is the ID. We call it name type. Okay, so you have single type. You have single simple type, and you also have equal. Okay, and then there are number. You actually get the number and you evaluate to the number. If the value cannot be evaluated, then it will set to 0, okay? And they are equal null type and new line number count, okay? And then error tokens, okay? So you can also build a Lexer. After you build a Lexer, and then you have the precedence level, okay? Precedence level from lower to higher, okay? The precedence level, and your initial name is empty, okay? And you have the assign statement. So this one actually is what put into the content-free grammar format. And the content-free grammar is put into here as dual. So this one needs a stack. And it is not part of Elixir. This one is actually the so-called, this one is the so-called push down automata or content-free grammar. We will talk about it in the next lecture, but basically we assign the T3. So T3 is you have A equals B, token 1, token 2, token 3. Token 3 assigned to the name of token 1. Okay, that is the assignment. Okay, something like that. Okay, that's actually name equals some expression. And this is a statement. Okay, this is a statement. And statement can be a single expression is a statement. So in that case, we just print it. Okay, this one is assignment, and this statement for with only one expression. So these are different statements. And you have expression with binary operators. Expression with binary operators. So expression with binary operator, including expression plus expression, expression minus expression, expression times expression, something like that. You will do evaluation for all of them. Okay. So here T0 is the left-hand side value. T0 is the left-hand side terminal, and T1, T2, T3. Okay. Something like that. And here T0 is your left-hand side tokens value. Okay, will be equals T1 plus T3 if the T2 token is plus. Okay, so this is the binary operator. So inner operator getting a minus. Okay, grouping using parentheses. Okay, so the expression value will be assigned to the left-hand side expression value. Okay. And then you have a single number expression you assign to it. So here you have different rule. Okay, this different rule in parser, we will talk about it. Okay, and also there's an error rule. And by using those rules, you can build a parser, and a parser using ex.yyef. Okay, you get a parser, and this parser you true. So this parser would use the token generator. Okay. Get the token, and the token will be evaluated by the parser, and it is true whenever you have the problem of calculator, and you will get the input and get the value. If the parsing is error, you break. Otherwise, you will use parser the pass to get a evaluation and print. So here, this one is what read. It is also a read, evaluate, and print and loop back. Okay, it's a read, evaluate, print, and the loop back format. Okay, so that's called calculated the PY. Okay, so let's look at this example. Here it has a more detailed file input and data. Okay, but let's look at this example now. So use this one. We actually open the folder and look into the print. Okay, so use this one as the folder, and we have this one called calculator.py. Okay, so right here you use the terminal. Okay, and you do Python. Okay, calculator.py. You get this one, and you say 1 plus 2 times 3. Okay, you get 4 times 4. 3 times 4 plus 2 times 1. okay, something like that, and you can actually do consolidated break it, okay? Okay, so that one is a parser example. It's a complete tiny calculator example, but in this lecture, we are not focused on the so-called parser yet. And I just give you a simple example of when you have the Elixir, it can be integrated with the parser and become a full interpreter. And that would be what we are going to study from lecture 12, 13 for the parser, 14, 15, 16 for the integration of such parser and Elixir. Okay. And there are some details you can study. And this is the end of our chapter 8b, the Elixir. So in this chapter, we go through the study of the regular expression and then put the regular expression into the regular expression functions and build in regular expression pattern object and use that to process the strings. And then we can put the regular expression into our Flex and Python structure, put them into C language, or you choose to use the Python Lex and EX in, you can use it in Python language as well. So this chapter A is on the automation of Elixir design. And compared to Elixir chapter sub AA, the lecture 10, that one is ad hoc scanner. Both can help you to design a Elixir, and both are a very popular way of doing it. Okay, thank you. Bye now.